Welcome everyone. Another video on AC machines and controls. So here we are looking at space vector modulation. In the past lecture series, we've been looking at different modulation strategies, how they look like in real life, and then how we can implement a sine triangle modulation and some of the basic ideas being the modulation strategies and the inverter, right? So this is a little more advanced space modulation strategy that is very popular because of a lot of advantages you have with this type of modulation scheme. Okay. Now, originally, I actually looked at the publication. This was published around 1986 by several German authors, Van der Broek and Stank, and this is a very nice approach to generate sine voltages, which will result in low current harmonics while being able to achieve higher modulation index. Okay, so remember, if you remember the third harmonic injection case, we were able to show that we can go higher voltage, higher phase voltage without being limited by the or for the same DC supply in comparison to sine triangle modulation. Third harmonic injection case was able to reach higher voltage at the phase level because your neutral point was being slightly moved. So similarly, this gives us such advantage, and it's the problem is approached in a slightly different way, and we'll go into details very quickly. Now, what we're trying here is, if you remember our space vector discussion from a couple of lectures back, we showed that we can set up currents such that it's a rotating vector in the spatial domain. We said, if we have phase A, phase B, phase Z, phase C, 120 degrees out of phase, combining the three, we were able to come up with a vector that is rotating. If you don't recall that, please go ahead and refresh that. It should show up in the playlist here. And similarly, in order to generate such current, we need to generate a voltage that is a space vector that's rotating in that in the space, right? So this is in that same concept into our modulation scheme. So in this video, we'll try to go all the way to explaining how the voltages are being generated and how is that relating to our inverter switching states. Okay, and we'll be able to show that by controlling the time you maintain or you sustain that vector, you are able to control even the intermediate voltages that you apply within each sector. So let's actually go ahead and start our discussion. Okay. All right. So what do we have? Space vector modulation. So here we are talking about the concept of modulation index, which is essential, which means how much of voltage with respect to the DC bus is being applied at the moment. Okay. So the absolute value of the modulation index can be found by square sum of the square root of these Q and D axis components. This will allow us to control the D and Q axis voltages that are in the stator reference frame, which means it's a rotating vector. We can even think of it as alpha beta frame, the Q, M alpha, M beta, which are rotating vectors, if you recall from our reference frame transformation video. Okay. Now, what we need to do is, in this case, we need to link our space vectors to the voltage source inverter, which might look like a daunting task, but once we're done with this discussion, you'll see that it's fairly easy to make that connection. Okay. All right. So first of all, let's look at the different inverter states that we are going to come across here. Okay. So let's actually go here. Now, let's consider just one leg for our understanding for now. And we have three of these in a three-phase voltage, three-phase inverter, right? And we are going to use a binary coding scheme. Okay, so let's say if you're going to keep the top switch on, that means this is going to be a 1. Typically, we don't like shoot through. We don't like to have both switches on at the same time. Therefore, we are assuming when the top switch is on, the bottom switch is off. Okay, bottom switch is off. So when this is 1, so the inverse of that is the bottom switch. And when this is 0, that means the bottom switch is on, because the inverse of 0 here is 1 for the bottom switch. Okay, so now if you consider each leg, you're going to have a 1 and a 0. It would look like this, right? So if you are looking at the case where we have 1 for one leg, right, you would see that your top switch is on, and then the bottom switch is off or open. Okay, and then for the 0 case, you're going to see that your top switch is open and your bottom switch is closed, that is on. Okay, and of course we're going to see some intermediate levels. If you remember from the previous discussion, you could see both switches open, right? Both switches open. They could be, that could occur in under certain circumstances, but they are very they're going to be very for a short period of time, which we can neglect. And then same goes for the short case. I hope this doesn't happen in practice, because this is basically shorting your DC bus to ground through the switches. So this is not desirable for our inverter. Okay, so these are the 4 states that we're going to see mostly, if you remember the discussions previously. But for our space vector modulation, we are going to be using these 2 states, 1 and 0, for a leg. That means if we have 3 legs, now we have several combinations that work with, and that by how the switches are turned on or off, we can control how the voltage vector is placed. Okay, because this, let's say we have one leg going to phase A, another leg going to phase B, another leg going to phase C. So by controlling the combination of those switch states, we can actually align or set up our voltage vectors. Okay, all right. So let's go here into the states. Okay, so let's go to the whole diagram here. Right now, I'm just leaving them blank. Well, we can use X's here because we don't know what the states are yet. So X, 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 right? So now for each switching state, we will define what switch leg 1 is on, what switch of leg 2 is on, what switch of leg 3 is on. So it's going to be, you know, 1 0 0, 1 1 0, 1 0 1, 0 0 1. So we'll have different combinations to work with. Okay, and then we typically split, you know, plus VDC minus VDC to go and analyze our voltages applied to the machine. Now, when we come here, when we set up a certain switch configuration, now here we are considering a balanced machine, an ideal case to simplify our analysis. The advantage there is when we have a balanced motor, we have 3 equal impedances, right? And then if we know the voltages that is being applied to each phase, which in this case, either a plus VDC or ground, or plus VDC by 2 or minus VDC by 2, either way you want to go, you're going to see that there will be a certain voltage across A, certain voltage across phase B, certain voltage across phase C. When we consider them to be, equal impedance, we can use voltage divider rule and come up with how much voltage is applied across each phase, assuming or with respect to the neutral. So we're going to use with respect to neutral because that's what the machine sees. Okay, so that's the plan going forward. We're going to look at a couple of different switch combinations and see how we can relate states to our inverter, or how can we relate the switching states to our vector. Okay, space. All right. So here we have a certain combination. Okay, so I'm considering this to be full VDC. You can even consider a half, VDC by 2 and VDC by 2 split. So plus VDC by 2 minus VDC by 2. Whichever way you follow, the voltages on each phase with respect to the neutral will not change. Okay, so here we have first switch on, so we have 1, right? And then 0, 0, that means the two bottom switches are on here. So in this, before we go and plot the voltages on the voltage plane, so this is our space vector or vector space that we're going to draw. How much voltage for phase A, how much voltage for phase B, how much voltage for phase C. We need to find out, or we need to calculate what they are, right? And looking at this diagram, we can see that on phase A, we have VDC, right? VDC is connected. And on phase B and C, we have 0 volts. Okay, we have 0 volts connected. So that can be used to understand this, right? So now what we can do is we can set this up. So this is what we need, right? For a balanced machine, these are of equal impedance. So I'm using Z1 here. Now we can do a voltage divider because this voltage is VDC. So if you use voltage divider tool, you will see that we have 2/3 VDC applied across this impedance or this phase. And since the other two are in parallel, 1/3 of the voltage goes there. That makes sense. Your impedance, when they're parallel, they get cut in half if they're equal, right? So you have 1/3 of the voltages here. Now, what happens is, if we consider neutral point to be, or if we consider the voltages on each phase with respect to the neutral, then what we can do is we can come up with a voltage value for phase A to be 2/3 of VDC. For phase B and C, negative 1/3 of VDC. Okay, so I hope that's pretty clear on how we came up with those values. Now what we need to do is we need to draw them on this vector space, right? So phase A, if we consider this 0, 0, 0, right? This is 0. We have positive 2/3 VDC, right? Let's consider up to this point VDC. So that means 2/3, that's about right there, right? So we have, this is phase A, right? So I'll try to stick to my colors here so that it doesn't confuse you guys. Now phase B, with respect to the neutral, we have negative 1/3, right? So negative 1/3, so this is the positive B direction. Negative 1/3 is, that means it's going to be in the opposite direction. Okay, so negative 1/3 VDC. And then we have on phase C, we have another negative 1/3. So this is phase C, then negative 1/3, that's going to be along this direction. Okay. All right. So we have these voltages need to consider is, okay, what is the total resultant vector? So that means we need to add the 3 vectors, right? Using vector addition. So we have 1, and then we can place the other vector here, and then the third vector. Or you can do this mathematically. If this is 1/3, right, then cosine, this angle is 60, cosine 60, cosine 60, you'll see that we get VDC along the phase A direction, because the vertical components cancel out, they're equal and opposite, right? So totally, when we place our switches in this configuration, we have the voltage vector being applied directly along phase A. Okay, so that means we have we can get the current to align, assuming very minimal inductance, your current along phase A. Okay, so this is how we link our switching states to the space or the vector space that we are going to analyze our flux vectors, current vectors, and all those vector analysis that we're going to do here. Okay, so what our vector 1 or phase 100 is going to generate the voltage along with. So that's going to be along phase B, sorry, phase A, right? That's for 100 state. All right. So now what we need is, we need a rotating vector. That means we need to move this vector in this circle. Now, how can we do that? Okay, let's see how we can do that. Let's consider switching state 110. Okay, 110. Now that means 1 1 0. So this has switched. So this is open, this is closed. So we get this combination, right? So phase A and B, they have 1/3 VDC, but phase C has negative VDC. So let's draw this. I think this is beneficial to for us to draw. So phase A has 1/3, positive 1/3, right? Positive 1/3. Phase B has, what do phase B have? Phase B positive again, positive 1/3. Okay. Phase C has negative 2/3. So that means negative 2/3, something like that. Oh, very nice, right? So now if we do the vector add for 110, we will basically get a voltage vector right along that. Okay, previously we got a voltage vector along phase A. Now we're getting a voltage vector along negative phase C. Okay, so we can now control, we move the voltage vector from A to negative C. So now that means by controlling the different states, we can align B, align it with negative A, align it with C, align it with negative B, likewise. Okay, so far we can only switch from here to here, right? We can keep it here, or we can switch it here, right? We don't have a smooth voltage vector yet. We know we can apply it here or here, and we have other combinations, right, that we can use, and we'll talk about them in a little bit, that we can use to align the voltage vector so that the current will follow. Okay, and among them, among those different states are 2 more important states that we have to think of. Okay, one is the 000 case. 000 case. So when we 000 case, that means all the bottom switches are on. Okay, if I look at my machine, all the voltages are zero, right? All the voltage, so phase voltages are zero. Therefore, we have a zero vector, right? There's no voltage. And then the other state is 1, 1, 1. So in the 1, 1, 1, all the phases are again at the same voltage, VDC, 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 right? Therefore, again, no voltage differential. The phase voltage is again zero. Okay, these are important states because they're going to be intermediate states that we're going to use to help transition from one sector. So we call each of them a sector to another sector. Okay, so we start at 0, 0, we apply this vector, go back to 0, apply the vector, and then we transition back. Okay, so let's see if we can go and look at this in a little bit more detail. Okay. All right, so this is what I was talking about initially. Okay, so we have now several combinations that we can use, and you are welcome to go see if these make sense, if these combinations align the vector along B, align the vector along A, align the vector along C. You can go ahead and do the vectorial sum and then calculate that, and then we call these state the sector 1, sector 2, sector 3, because this is important, especially when you have information from your control system. For example, your field-oriented control system, it will generate EQ and VD, VQ, VDS, QS commands, VDS commands, along with you have a theta measurement. These are in a rotor reference frame. With the position animation, you can transform to V alpha and V beta, which will tell you which sector you are in or which sector you would be generating your voltages at, your controller. Now, once you know which sector you want to be at, and then using the magnitude of your voltage vectors, you can generate, you can set up timings for each of these vectors so that you use a combination of the two vectors to generate an intermediate vector. Okay, so that's called fast averaging. So for example, we know that by averaging PWM we can generate an average voltage, right? So by using, let's say we apply along this vector for 20% of the time, and then we apply an 80%, so we take a PWM period, and then we hold this vector 20% of the time, okay, 20% of the time, 80% of the time we hold it along this. So the sum, if you do the fast average, that voltage vector will be more aligned to the 110 state because we had more 80% of the time on this state, right? So by controlling that timing, how long do you hold each sector on within a PWM period will enable us to play the vector at intermediate levels within a sector. Okay, so that's how that time averaging to move the vector from, say, 100 to 110, and now we can get a rotating vector that will result in a rotating current vector, which will in turn result in a rotating flux vector. Okay, so in order to understand this cyclic process, let's see what we need to do to set up at least, I'm trying to find the right word here, the sequence that we have to follow in order to get to this state. Okay, so let me see if I can find my inverter, well, I'll draw them here. So initially we start with 0, 0, 0. So that means we have the bottom switches. So sorry, no, not this. So top switches open, right? The top switches open, bottom switches close. Okay, so we start at the 0, 0, 0. So now then we go 1, 0, 0. That means we hold these two switches on. What we do, we change one leg. So the importance of this process, this method, is we are only changing one switch at a time. And this is actually very helpful if you go, when we look at the next page on the PWM sequence that we are going to use. So 1, 0, 0 means this is going to transition to this configuration, right? We changed one leg, we switched one leg. Okay, so we transitioned into this vector. So this means vector is going to be, initially we started at 0, 0, and then now we are applying along A. This is our A direction, right? And then we are going to switch to 1, 1, 0, 1, 1, 0. So 1, 1, 0. That means we're going to transition to, again, you can see that we are only switching one leg. One, 1, 0. This is open, this is closed. 1, 1, 0. 1, 1, 0. 1, 1, 0 is basically what? 1, 1, 0, if you recall from our vector space diagram, that's this sector, right? So that's that vector, right? So that means second period or second brief moment of time is going to be along that. So 1, 1, 0. This is 1, 0. Tends to align with A. This is negative C, right? So we call it for this time, and now we switch 1, 1, 1. What's 1, 1, 1? 1, 1, 1 is all the top switches closed. All switches closed. So that means again we come back to 0, right? And now we go in return. 1, 1, 0, 1, 1, 0, 1, 0, 0. We are back at 0. Okay, so this is 1, 1, 1 and 0, 0, 0. So during that cycle, we have to apply this voltage vector for some time. We don't know. We will see that PWM sequence. We were able to access this. We went to this. We came to 0 for a brief period, and then we went back and returned. Right? Similarly, we can, if by modulating the amount of time or by controlling the time you hold each vector, you can let your you can place the resulting vector or the fast averaged voltage vector anywhere you want within this sector 1 by controlling these two states. Similarly, by controlling this and this 1, 1, 0 and 1, 0, you can place it within this sector with a certain resolution, right? That resolution is based on the frequency that you are generating and your switching frequency, your carrier frequency, right? You can do the same for this sector. You can do the same for this sector. Okay, so that way you can generate rotating vector, right? One leg is changed each time, and then I've been talking about duration of on time of each vector. So how long do you hold that vector? So when you are implementing this algorithm in a controller, this is actually controls. This is what controls how you're going to move the vector, right? You're calculating for on times in the algorithm. Okay, determine how am I going to move this. So for how long do I need to hold one vector in place? Okay. So you can see here now, this is actually linking all what we have been discussing so far, right? So you can see that this is one single PWM period. Okay, one single PWM period. You can control each of these time intervals, right? There, see, it's a strict shape. So this is basically coming from triangular wave, right? And we are talking about each leg. And we are showing you the signal that's applied to the top switch, which means the bottom switch is the inverse of this. Okay, and then each of this is a period. See here, we have 0, 0, 0, right? By adjusting how soon you're going to turn on, you can control that 0, 0, 0 state. And then here, the second state is 1, 0, 0, right? 1, 0, 0. So if you go back to our diagram, 1, 0, 0, 1, 0, 0, that's it, right? Now we can control when this is going to turn on, right? By controlling that, you can basically control how long will the inverter stay in this 1, 0, 0 state. Okay, and then we have 1, 1, 0 state. With this, you can control how long you stay in this state, right? In that state. Likewise, now you can control these timings, and then after 1, 1, 1 state, you're going to go back to 0, 0, 0 in the same order came to 1, 1, 1 state, like the same sequence. So by controlling that, now you can place the vector as well as control the amplitude of the vector as well. Okay. All right, so the amount of time spent on it can be controlled, and then if you see the fast average, that determines how much voltage is being applied to each phase of the machine. Okay. All right. So I think that's it. So what we learned is actually very interesting. We were able to go from our inverter switching states to the PWMs that we apply to each leg, which is linking us to how to generate the voltage vectors. Okay, so if you keep on for 100% of the time, then you're going to be along phase A, right? And then if you are switching it for 50% of time for A and 50% of the time for B, then you're going to be right in the middle, right? Because the sum of the two is that's where you're going to get to, right? And let's say you want to control the amplitude. How do we control the amplitude? Instead of applying 100% duty along this, you divide that time. Let's say, let's go back to this diagram, right? 1, 0, 0 is what determines how much voltage that you apply along that vector in the vector space, right? And we have two conditions here. See, we have 1, 0, 0, 1, 0, 0, right? Now, if you set 1, 0, 0 for a shorter time instead of holding it for a longer period, means you're going to apply lower than the full VDC onto all along that vector. So that's how you control the modulation index. And by controlling the two phases, you can move the vector in this vector space. Okay. So it comes down to timing calculations that will be written into your PWM registers that will set up that, or that will drive the individual switches to be on or off for a certain period of time. Okay, so hopefully this helped a little bit clarify the space vector modulation strategy. And there are different processes, different algorithms that they use to calculate timing values. I'm not going to get into that in this discussion. If you want to, you can look up Texas Instruments Control Suite or Microchip. They have a software library that explains this in detail in terms of timing calculations if you are trying to implement that. Okay. All right. So I'm going to wrap it up. Then if you need if you have any questions, clarifications, feel free to comment. Let me know. You can contact me via email. And then, if there's any more information is needed, I'll be happy to prepare additional video about this technique. Okay. Thank you so much.